When I started looking into vector databases, the problem I had is that nobody wants to tell you how they work internally. Like if you go to YouTube, for example, which is the place where I get a lot of information, most videos talk about vector databases as being really important, being really fast, being critical for building AI applications, but nobody wanted to explain how vector databases work internally. So if you are a nerd, if you like to sort of like pull the curtain and take a look at what's happening behind the scenes, with this video, I want to show you just a quick explanation for 5 years old of how you can have a vector database do what they do best, which is storing and retrieving massive amount of vector in a very short amount of time. So if you are building with AI, if you've seen how to build a rack system or to store any one of these embeddings that we generate using large models, you understand already what the challenge is, right? So by the end of this video, I want a couple things. Number one, I want you to have a better idea, a better understanding of how vector databases work. Number two, I want to show you one particular example of how you can start using a vector database right now. And all of the code that I'm going to show you here is going to be in Python. And by the way, I really, really hope you like my shirt. I'm not recording today with one of those boring black t-shirts. So something different. If you don't like it, just let me know. I'm gonna go back to my t-shirts because I just want to make you happy. All right, so a couple of recommendations first. I'm going to start talking about FAIS, which is the Facebook AI Similarity Search idea, or let me call it library, okay, because it's a library. So I'm gonna talk about FAIS here. I'm gonna show you how you can use FAIS on your project. I'm gonna talk about 3 different algorithms so you understand the progress. And here is an article that I found on the Pinecone website that is amazing to understand everything that's going on here. It's called Introduction to Facebook AI Similarity Search. That's FAIS. So this is great read. By the way, Pinecone is the database, the vector database that I'm gonna show you how to use today. It's probably the most popular one, at least it's one of the first that came out as soon as this AI revolution started. It's the one that I've been using throughout most of my videos here. So I'm going to show you how to use it. They have the ability to generate these databases serverless, so you don't have to keep a server around. It's super cool. So we're going to get there. The second thing, or the second recommendation is the FAIS library paper, and you can search for it. Just search for FAIS paper. And again, this paper here, it's written by FAIR or Facebook. It's just the AI department at Facebook. And it covers all of the technical aspects of FAIS. Okay, so that will be the second recommendation for you to read. So let's get into the code here and let's start sort of like going line by line and trying to understand what I'm going to be doing here. So first of all, I'm going to start with a data set, just a CSV file of sentences. These are random sentences. Facts. A little girl is smiling and running outside. Just sentences, random sentences. And I have 1,000 of them. Okay, now I want you to imagine that these sentences are, for example, summary of books. Okay, so instead of just the title of the book, just imagine that this is the summary of a book. Okay, and we work for a library, and we want to give people the ability to search our library, thousands of books, in this case 1,000 books, not just by keyword search. Let's say somebody wants to learn about soccer. Okay, I don't want just to return as a search result any books that mention the word soccer. I want to go beyond that. And I want to give people the ability to search for more obscure ideas that might be contained in the book or in the book summary, but not necessarily using the same keywords. Okay, so that's what semantic search is about. That's when you have your mobile phone and you go to your photo library and you type pictures of the ocean, and some ocean pictures will come up. Like, you did not tag those pictures, but there is an algorithm that generated information about pictures, and now you're able to search over that information. So that's the exercise that we're gonna try to solve here. And I'm gonna do that starting with these 1,000 sentences. So how do I extract that information? How do I get these sentences and turn them into something that later on I can search on top of that something to generate good results? Well, here in AI right now, we call that embeddings. And specifically for this example, what I want to do is use OpenAI Embeddings API to generate those embeddings. And I have a separate video. Actually, I have like a couple of separate videos that focused on embeddings. That's, again, an entire different discussion. But suffice to say, if you don't know what I'm talking about, an embedding is just a vector of numbers that represent coordinates in a multi-dimensional space. Just like latitude and longitude represents coordinates in a 2D space in 2 dimensions, right? Well, these embeddings, think of them as coordinates in a world that has multiple dimensions. Actually, here for the OpenAI API, the embeddings that we're gonna get back have 1,536 dimensions. So that it's just, it will blow your mind if you try to think about that, but that's what they are. The main idea of these coordinates is that similar concepts will be located very close in this multi-dimension space. So if you have a sentence or a book summary of soccer, that book summary will be located close to a book about soccer balls, a book about players, a book about sports, right? They're gonna be close together because they represent similar concepts. And obviously, concepts, ideas, sentences that are not related, they're gonna be far apart, okay? So the code here, I'm going to start by loading the sentences CSV file in memory. I'm using the pandas library. Very, very simple code, just one line of code, loads that into memory, and then I'm displaying here the sentences with the head function just to make sure that I did a good job loading them. So after that, I'm going to be generating embeddings for those sentences. Now, keep in mind the code here that I'm showing you here, you're gonna find a link to that code in the description below of this video. When you open that code, you will already have the embeddings because I generated for you. You don't have to regenerate all of the embeddings. It takes, I don't know, maybe 5 minutes to generate the embeddings for all 1,000 sentences, maybe a little bit less than that. And obviously you're gonna have to pay money because generating embeddings with the OpenAI API is not free. But you don't have to do that because I already did that for you. So there must be a file that's called, let me see what the name is. It's called embedded sentences, and that file will contain the 1,000 sentences plus the embeddings. If you wanted to run this code using a different library to generate the embeddings, then yes, you can start with the sentences one. You don't have to use the OpenAI embeddings API for that. All right, so let's get back to the code. I have a quick function here, and this function is just gonna use the OpenAI API to take a sentence and generate an embedding. So that's gonna communicate with OpenAI. I'm gonna give it a string, the sentence, the girl is beautiful, and then I'm gonna get back my vector, which again has 1,536 dimensions. So this cell here checks for the existence of the embedded sentences CSV file. So if it already exists, I'm not gonna do anything with it. I'm just gonna load it. So I have already the embeddings. If it doesn't exist, however, I'm going to be generating the embedding. So you can see here, in the case the file exists, I'm gonna load it in memory. And then I'm going to term, just because this is a CSV file, when I read the CSV file in memory, I want to make sure that the column representing the embeddings is a NumPy array. So that is what I'm going to be doing here, just applying an eval, just passing NP array. So that's converting that column into NumPy array. If the file doesn't exist, okay, then I'm just going to be calling the getEmbedding function for every one of the sentences and adding that result as part of the embedding column. Okay, so that is what's going to happen in this cell. All right, so all of this is preparation, okay? We haven't gotten into the vector store part yet. All right, so here, when I get here, I'm gonna be adding a new column. So I'm gonna be using this ID column later on. I'm gonna be adding that column and it's just a consecutive number, okay? So up to this point, I have the sentence in my data frame. I have the sentence, the original sentence. So I'm gonna have 1,000 of them. And look at this. These are the embeddings, okay? So they're gonna come in an embedding column. Let me add a new thing here. By the way, I think I have to rerun all of this if I want to do something with this. Let me see. All right, so I'm going to do the following. Dataset.ilog. So I'm gonna just get the first one, that embedding, just so you see what's inside. You can see it's an array of numbers. Those are the coordinates, again, in this fictitious multi-dimensional space. And those coordinates are positioning that sentence in that space, okay? That's it. If I look at the length of this array, I want to see how many coordinates there are inside this array. We have 1,536 values here. So it's a long array, and that is as determined by the OpenAI API. If you're using a different algorithm, you might get, or a different API to generate embeddings, you might get different coordinates. In the video that I posted, I think last week, I generated embeddings for images. I built it like a network from scratch. And those embeddings had 128 coordinates. So it's just quite smaller than this. All right, so all good. Actually, I created this cell, but I was already doing it here. As you can see, I'm just creating a variable here that contains the 1536 dimensions because we're gonna use that later, all right? So far, we just generated the embeddings. We're just ready to start doing stuff. Now, what do we do with those embeddings? Well, we have 1,000 of those embeddings because we have 1,000 rows. So what can we do, or how can we find in that array? Let's say the customer comes and they want to buy a book about soccer, and we want to find everything in that array, in our list of embeddings, that is similar to soccer, that request coming from the customer. So what we can do is, well, we can generate the embedding for the query that the customer wants to answer, which is books about soccer. We can generate an embedding for that and then compare that embedding. Remember, there are coordinates with every other embedding that we generated. We have a data set right now with 1,000 of them. So we could compare the embedding generated for the user's query with every other embedding in our list and grab the ones that are the most similar, meaning they're close to each other, okay? So this is like looking on a map and finding anything that's very close to the location of the embedding that we are going to generate from the user query. Everything around that area that is similar to what the user is looking for, okay? That is the idea, and that's it. If you can build that, and it's very easy actually to build, you can just compare these two embeddings by using a concept that's called cosine similarity. So if we go here to our browser, so we can find the cosine similarity formula. There is a Medium page. I'm not going to open that. Let me open here Wikipedia. So by implementing the cosine similarity formula, by the way, you don't have to do it manually. There are libraries that already do that for you. You can compare two vectors. And the closer they are, the smaller or the larger the cosine similarity will be, the more similar they will be. And that's it. There is a problem though, and that is where vector databases come in. Well, imagine if I have 1,000 books. Imagine having to go and take the input embedding from the customer query and comparing that to every one, or computing the similarity from the query with every one of the embeddings that we have stored in that database. We will have to do, in the worst case, 1,000 comparisons. That will be very, very slow. Not for 1,000 embeddings, but if we're talking about a large library, we might be talking about tens of thousands of books. Or if you're talking about documents for your rack system, your rack application that you're building, we might be talking about millions of embeddings. So you don't want, every time you want to search something, you don't want to start from scratch, right? You don't want to have to compare one thing against everything else in your database. You need a faster method of doing that. And that is something that vector databases provide, right? So a vector store will give us that ability to search really, really fast. And that is what we're gonna see right now, how it works. So in order to get there first, I'm going to just use the files library here, all right? So to install files, by the way, there is a requirements.txt file. And that file here, you see that line 4 is files CPU. I'm installing that on my Mac. Files also works on the GPU. So if you have an NVIDIA computer, you can install the GPU version of this. I have not tried that on my M3 Mac. It might work, the GPU one. I have not tried it, so I cannot speak for that. So anyway, I'm going to use files, and this is the way, or this is what I'm going to be using. So first of all, I'm going to grab the list of embeddings from my data set, the column of my data frame, and I'm just going to generate an array with all of those embeddings. And by the way, if I execute this, let me just make sure that we are on the same page. How many embeddings do I have? Well, this is an NP array, so I can do shape. And we can see that we have 1,000 embeddings, and each embedding is 1536. So that makes sense. That is what I generated by just doing this here. So here is the query. This is sort of like the template that we want to search. I love soccer. That's what it says. So I want to return from my list of sentences anything that is related to I love soccer. Not anything, but I want to return maybe the top 4 documents that are related to I love soccer. So the first thing, obviously, is I'm going to generate an embedding for that. And I'm using the same function that I defined before. So I'm saying, hey, just give me the embedding for I love soccer query. So I'm just going to make sure when I print this out, I should get 1536. Yes, so that's an embedding. And this thing here is just going to be an array, obviously. Here you have it. So the entire list of coordinates is in XQ here, which represent the embedding of my query. All right. So first, I'm going to be using the index flat L2 algorithm as a vector store. So imagine a vector store. This is going to be in memory here, obviously, but a vector store that is going to be using this algorithm. So this is what's cool about this algorithm. It says flat because I'm storing my vectors, the 1536 sized vectors, just like that. And it says L2 because that's the algorithm, is the Euclidean distance, or L2. That is the algorithm that is using to search for that vector. Here's what's interesting. When you're using an index flat L2, there's nothing fancy going on. Behind the scenes, this is just a list of all of the vectors. And when we search that list, it's going to go one by one, finding anything that's close to the query that we're passing. So nothing fancy here. All right. So I'm going to create that index with those dimensions. So we specify here that we want 1536 dimensions, and I create that index. And I'm going to call isTrained. You're going to see in a few seconds why this matters. But when you're using a flat L2 index, well, it is trained. You don't have to do anything else because, again, all of the content is just going to go inside, and that's it. It doesn't matter where the content is. So this is going to be not slow, But as we add more embeddings, this is gonna get slower and slower and slower because it's just like looking on top of an array, all right? So I'm gonna add all of my embeddings. So let me execute this cell. Here I'm gonna add all of the embeddings to this index. And then I'm just gonna print how many items are inside my index. So I have 1,000 items. Awesome. And now I'm gonna perform a search. Okay, remember this search, because this is a flat L2, this search is just going one by one, comparing the distance and then returning the ones that are the most similar. So I'm gonna do my search. This expand dimensions here, this is just so I can get the query, the embedding, and turn it into an array with one item and the 1536 dimensions on the other one. That's nothing fancy. It's just, I'm gonna call it plumbing that I need to do in order to get this working. So I'm gonna pass my query. This is what my query is. And I'm going to say I want k equals 4, meaning give me the top 4 documents that are related here. So if I execute this, when I execute that, you get these 4 documents. Look at this. Oh, by the way, what I get back from that search, so I get something here that I'm not gonna use, but I get the indices of the documents that did I spell that right? Yes, I think this is indices. So I'm gonna get the indices of the documents that are a match for my query. Remember, my query was I love soccer. What I'm getting back is a man is punching a soccer ball, a soccer player is sitting on the field, and is blah, blah, blah. An opponent is tackling a soccer player. Great. So these are the top 4 sentences from my list of embeddings that are the most similar to the query that I passed. So using this technique, so far, I can do that semantic search, which is great. The downside, again, is that this is a flat L2, so it's not gonna scale great. The more documents we have, the slower this is going to get. So we need something better, okay? And that is where the IVF flat comes in. Again, the flat part indicates that we're still storing the full vectors, but now we're gonna use a very cool technique to make that search faster. So we don't have to go and make a comparison for every single position of our list of embeddings. So this here is a Voronoi diagram. I don't know how familiar you are with them, but this is the main characteristics of them. The dots, the black centers here are centroids. Any point within that cell, for example, this cell right here, any point within that cell is closer to the centroid that's in the middle of that cell. Now, this is a diagram that I drew by hand, so this might not be accurate. Don't read too much into it. This is just a comic diagram that we drew. But just believe me, in the real life Voronoi diagram, any point within this cell here, the closest centroid is the one that belongs to that point. Okay, this is super helpful in a bunch of different applications. Just to give you one idea, imagine a city where those centroids represent the location of the fire department truck or an ambulance. So if anything happens within that city, we immediately know which post is the closest, like where the fire truck should be coming from. Because this, if it happens right here, right in this point, well, this is the location that's the closest to that point. If it happens right here, well, this is the location that's the closest, right? And we can create in a Voronoi diagram, we can create as many centroids as we want. So the idea and the reason I'm explaining this to you is because this new algorithm that we're gonna see right now, this new index way of organizing an index, is going to use this same idea to cluster related embeddings in a way where at the time of searching, we don't need to search or compare every single embedding in our list. We can just go to one of these cells and do a comparison right there. All of this is gonna happen internally, by the way. So that is what the IVF part comes in. Okay, so here's how it works. First, I'm just gonna create 20 centroids. So that is how many of these black dots I want for my index. And obviously, the more you create, in order for them to make sense, you need to have more data. Like in this case here, I have 1,000 sentences, so it wouldn't make sense to just create 100 centroids. Smaller number is gonna be better. It's just gonna be a trade-off. So within every one of these cells, right, I'm going to be organizing the data using just a flat L2. So I'm still going to be using Euclidean distance to find similarities, and it's going to be flat. So that is what the quantizer comes in. So within a cell, I'm going to be using a quantizer here, which is the index that we just discussed. For the creation of the overall index, I'm going to be using this new format, which is the index IVF flat. Right, so I pass my quantizer, I pass the how many dimensions I want, and I pass the number of centroids, which is the number of black dots here. Now, if I execute is trained now, it says false. This is an index that needs to be trained. Now, why does it need to be trained? Well, how are we going to organize the information here? We don't know. So we need to add data and train it with some embeddings so it knows the index understands how to organize all of that information, okay? So how to put all of the data around those centroids, okay? So that is what we're gonna do right now. I'm gonna train my index with my list of embeddings. And now when I execute this is just super fast. When I execute that, now it says that the index is already trained. So now I can add my embeddings and just compute how many do I have. It's 1,000. Something here, obviously, you don't need all of the embeddings to train your index, but why not? In this case, you can train your index with half of your embeddings if you have too many, just with some of them. Something that's representative of everything that you're gonna see, that's good enough. As you keep adding embeddings to your index, they are going to be positioned correctly. So all of that's gonna work. Let me just do a search now. Search works exactly like before. I pass the query or the embedding of the query, and I pass how many items do I want to get back. And this is gonna give me the indices of all of those matches. Notice something though, when I execute this query, you are going to see that I'm returning sentences that look related, but they are not the same as the ones that I returned before when I didn't have anything fancy. So the ones that I returned before, a man is punching a soccer ball, a soccer player is sitting on the field. Let me see now. An opponent is tackling a soccer player. I think that one was up there. The crowd is watching a football game. That is different. By the way, notice this. A crowd is watching a football game. There are no words there that match my query, which is I love soccer. No words, but still it recognizes that football and soccer are kind of the same thing unless you are from the United States, which is soccer and football is football. For the rest of the world, they are the same thing. A football player is running past an official. You see here that I'm getting different results. Why? Well, because the way now the index is organized, the centroids here give us a trade-off where we get a much faster search, but the information might not be as accurate as if we go just with a flat array or flat index. So we need to keep these two in mind. Do you want faster, more accurate, or faster, right? And depending on what we need, we're gonna organize this index. One more thing, by default, when we do this search, what is going to happen internally is that we are going to return similarity or similar documents from one of these cells. But we can change that. For example, we can say, hey, find the position, the cell where you're gonna be looking at, but not only that cell, but get cells that are neighbors of this one here. So we can extend that, and we can do that using a property that I'm gonna have it here somewhere. It's called nprobe. So in this case, I'm saying don't get your results only from the cell that matches the query. Get your results from 5 neighbor cells as well, okay? So by doing that, I can execute my cell, and now you can see that the results are a little bit closer, Maybe the same? Probably not the same. A group of men is playing soccer on the beach. Let me see. A group of boys is playing soccer on the seashore. They're not the same, but they're closer to the original one. And the bigger I get, or the larger that number is, the closer it will become to the optimal results, if you will, right? Because I'm extending the search. Again, this is a trade-off. By doing this, my search is going to get a little bit slower, but the results are going to be a little bit better, okay? So that's sort of like the trade-off. So let's see the final one, all right? The final optimization that we can add to this algorithm. These are just three. There are multiple algorithms, but I just wanted to explain these top three. So the next one is IVF, but now it's not going to be flat. We're going to use product quantizer. So this is what that means, okay? So far, we've been talking about, we modified the index, but we stored the 1536 dimensions of our vector just like they are. Just we store all of that data. How about optimizing that as well? So how about creating sort of like an intermediate representation where we can actually search much faster? Instead of storing 1536 elements, we're going to store something else. And that is what this algorithm comes in. So this is what's going to happen at a very high level. And this picture here is a modified picture from the article that I show you. I tried to make it a little bit more clear, but we're going to get our original vector. And again, think of this vector as the 1536 elements. We're going to slice those vectors. So every component, every coordinate is just going to have a group of that coordinate, the first coordinate, and a group of the second coordinate, right? So that's what this line now represents. Notice how they are split, right? They're not part of a vector anymore. I have groups of sliced vectors, and I'm going to cluster those groups. Just like we did for the index using a Voronoi diagram, I can cluster them, and then I can grab the centroid of that group, and I can create a new vector, but now every position is just going to use the centroid. It's not going to use the actual value. It's just going to point to the centroid of where that value belongs. By doing this, we're quantizing our vectors to a much more manageable scale, and it's way faster to search. So again, I don't have here any, didn't want to build any way to just do the comparison because I had to just create millions of embeddings in order to make this a little bit slower. But the more optimizations we add, again, the less accurate our search is going to be, but the faster it's going to be. So we can, in fact, search millions and millions of vectors like really, really quick by doing all of these modifications. So let's see the code here. So for the code, I'm going to be using the index IVF PQ. It's not flat anymore. Now it has the PQ, which is product quantizer. That's the index that I'm going to be creating. I pass the quantizer that we create before, the embedding dimensions, the number of centroids. I'm going to keep the same number of centroids, the 20, the code size, and the bits per centroid. So these are the two parameters here that we're going to be using to decide how much we're going to quantize this. And there is a formula here. I don't remember actually the formula, but in the paper they explain what the formula is, which is what you need to keep in mind in order to give them this size. And they depend on how many items you have. So that will depend on how much you can actually compress these vectors here. Here is my index. Again, if I execute this, the index is not trained. We also need to train it, obviously. So here I'm training the index. I'm adding all of the data, and I'm going to execute this. And here we are with 1,000 elements added to this index. And now I'm just going to keep the probe in 5, meaning return any matches from your cell and 5 other cells around that cell. And I'm just going to do a search. And again, everything else is going to work the same. All right. So this is how, or this is an idea, or you can get the idea here of how these databases work internally. This is an algorithm that they use internally to make all of these operations extremely fast. Okay, so let's use one of those, or one of these vector store databases, which is Pinecone. Like I mentioned before, Pinecone is, I think, from my point of view, probably the most popular of these vector store databases. They've been around forever. Right? Since I started doing this AI stuff, I'm hearing about Pinecone. Very, very simple to use. Here, I'm going to use Pinecone directly just to store the data and just to do a search. That's it. It's going to be quick. But Pinecone also integrates with LangChain. So if you're using LangChain, obviously, they have a way to integrate with Pinecone. To use Pinecone, you need an API key, which in my case here, I have it as an environment variable. So you can go to pinecone.io. Let me see if I have it open here. I must. Yes, so right here, this is my Pinecone account. You can create an account for free and you can get an API key right here. With that API key, you add it to an environment variable, which is Pinecone API key, and that's it. That API key is the one that you're gonna just create your Pinecone database, okay? So here I'm creating my database. Here in code, you don't have to do anything else in the website. That's what's great about it. You don't have to just mess with it in the website. Just in your code, you can just define your database right here. Here is something cool that it's now available for everyone, which is great. Pinecone, you can use it serverless. What does that mean? Well, you don't have to spend any time dealing with servers or configuring stuff. You can just from your code, immediately on the fly say, I want to create a new Pinecone vector store database. Here is my data, and that's it. And it will immediately give you a serverless database that you can start using, delete it when you're done, whatever, right? So in my case here, I'm just creating one serverless spec. It's gonna be hosted on AWS, which is really cool. And then the region is gonna be US Eastern 1. I live in Florida, so this is the closest that I have. Pinecone made this for AWS available in a bunch of regions. You also have US West 1. You can find where else they have this available. But in my case, just very simple. Again, it's just, this is the specification. I don't have to go to AWS. I don't have to configure anything. All of this is gonna work transparently for me. So after I have that, I need an index. And again, we just talked a bunch about indexes. So I need to create an index here, and I'm calling it underfitted. That's the name of this channel, random sentences, because just those are random sentences. But I'm gonna create my index. If my index does not already exist, the reason I ask this is so I don't try to recreate the index again and again. Right? I can just call, hey, database create index. It's very simple. I'm just gonna pass the name of the index. How many dimensions do we need? We had to do the same thing with when we were using pies. You always have to specify how many dimensions, 1536 in this case. What is the metric that you are going to use for this index? I'm using here cosine similarity. Let me see what else is supported here. So if I go inside here, can I change it? Well, maybe I can try to create an index here. Okay, so you can use Euclidean distance, okay, which is the L2 that we saw for pies. You can use the dot product or you can use cosine similarity. My recommendation is for you, unless you know better, my recommendation is to stick to cosine similarity. There is actually a recommendation when you're working on an AI application for you to use the same metric that the model that is going to be using your code or that you're going to be using in your code is using. So in the case of OpenAI, that will be cosine similarity, so you should stick to it. All right, so let me get back to my code. So I'm specifying cosine similarity, and now I'm passing the spec, the serverless spec that I just created. By executing this line here, oh, by the way, it's just the time.sleep, Pinecone recommends that just to take a second for the system to sort of like assimilate the create index, just wait for a second here before you do something else. That's gonna give it a time to catch up. So when you execute this, and I'm gonna execute it myself, I have to execute this, and then this, and then this. When you execute this, if you don't have an index, then you're gonna be creating that index for the first time. So it's just gonna take a few seconds to finish. This here is just now grabbing my index. It already exists. So I can do describe index stats. And when I execute that, you get, okay, so dimensions 1536, namespace vector count 1,000. The reason I have 1,000 vectors is because I already uploaded the information. So I'm not uploading it here. I already have all of the information up there. Total vector count 1,000. This code, I'm not gonna spend too much time on it, but these two cells are going to upload the data for you. So when you execute this notebook, this condition asks whether or not you've uploaded all of your data. If it's 0, that means there is no data. It's going to upload the data. And in order to upload the data to Pinecone, something super cool is that you don't need to upload embedding by embedding. I have 1,000 here. Imagine having 1 million embeddings, and you have to sort of like insert one of each of those embeddings. You don't do that. Instead, you can upsert batches. So you can just grab a bunch of embeddings at the same time and just send them. That is what I'm doing here. That is why I have this iterator and vector functions that I created here, just to format my data set in the format that Pinecone expects and pass the information that way. By the way, what is that format? Well, if I go here to Pinecone, I'm gonna go back to my database. Notice that I'm storing an ID and I'm storing the metadata as well. So I'm passing all of that information here. I'm passing the ID that we created at the beginning. I'm passing obviously the vector, that's the embedding. And I'm also passing like the metadata in this format, which is the sentence and the value of that sentence. That's why you get here the metadata contains sentence. So why is that important? Because whenever you do a search and you find the similar vectors, you want the ability to just read that metadata. You want the ability to say, okay, what was the original sentence? Not the vector. The vector is just numbers, coordinates. I actually want the real deal. In the case of the library, you could store here the name of the book. So the sentence could be, for example, the book summary, but you could store here the name of the book, the author, the location within the library, whatever information you want to store here, that could be part of your metadata. So at the time of doing a search, you're gonna get back anything that you need. All right, so after uploading the data, I describe the index stats again, and then I do a query. Again, it's just very simple. I'm just saying, hey, just use that index and query my vector, this XQ. You might remember that from before. That's just the embedding of I love soccer. Give me 4 items back. And please include the metadata when it comes back, right? And then I can just go through the matches and I can just display the sentence coming from the matches. So if I run this, boom, I get all of that. This is not in memory. Now this is actually going to AWS somewhere in the world, I don't know where, US East region, and it's actually returning data from 1,000 embeddings. And again, it's 1,000 embeddings, not a big deal, but this is darn fast. That you can do similarity search that fast is just mind-blowing. Let me just create a new one and then we're gonna wrap it up, okay? So my second query is going to be, I don't know, I like animals that eat too much. I don't know. I'm just gonna create something like this. We're gonna need to just generate the embedding. Copilot is helping me out here. That will be the embedding. And now we just need to do a query. So let's do response equals, let's see if Copilot wants to help me. Yes, we're gonna be searching the query, the Pinecone index. We're gonna be passing the query. We want, let's say 3, and yes, we want the metadata. And now we want to display the results. Okay, so I'm going to execute this. Boom, it's just that fast. Okay, so it's just incredibly fast searching, and the results are the animal with big eyes is voraciously eating. Look at that. That is a beautiful example. I'm getting goosebumps here, okay? So that's a beautiful example of how these things work. I'm saying I like animals that eat too much, and eating too much is precisely being voraciously. Some kittens are hungry. Yeah, that's related. Someone is cleaning an animal. Less important. I wonder what would happen if I say 5 here. Like it's gonna start returning. A lemur is eating quickly. A cat is eating corn on the cob. Well, maybe I'm gonna give it. So that's it. So if you are building an AI application and you really need to store all of these embeddings, now you know what to do. My recommendation is usually Pinecone, but hopefully by now, there is one more line. I'm gonna tell you what it does right now, but hopefully by now, at least you have a better idea of what's happening behind the scenes. Why are these vector stores so darn fast? And it's because the algorithms that they're using are very clever and organize the information in a very clever way so they can actually return matches really, really quick. The last line that I have here It's just how to delete an index. So I'm going to execute it right now, and my index should be, boom, done. So all of the information that I created on the fly is now gone. If I go to Pinecone now and I refresh, I hope that that index is not there anymore. And as you can see, boom, gone. So hopefully you enjoyed this video. Give me a like down there somewhere so I can keep producing content like this, and I'll see you in the next one. Bye.